Before going to start this, let me introduce myself. Myself, Dhanashree Mam. I completed my MSc in Mathematics from Mumbai University and also having 13 plus years of teaching experience, and I mentored more than 10,000 plus students for the engineering. And let me introduce myself. My name is I completed my MSc in Mathematics from Mumbai University and also having 13 plus years of teaching experience. I mentored more than 10,000 plus students for the engineering. Okay. Now let's I will tell you how to install the Unacademy's learning app. First, go to your mobile's Play Store app and then search Unacademy's learning app. In that, you will find out like this. The arrow is linked here, Unacademy learning app, and then install the Unacademy's learning app. After that, मैनेज योर गोल हियर जैसे कि हम लोग यहाँ पे अभी मैनेज की है GATE and ESE. You can manage your goal here so that it will give you complete course. Now here you can choose any one of the subscription plan, either plus subscription, free courses, special classes, anything that you want to choose here, so that you will get a proper subscription plan here, and then press the get subscription button icon. After that, you have to take the subscription plan either for 24 months or for 12 months. It is depending on you. If you are going to prepare for the 10 date 2022, then I will suggest you can choose a 24 months plan so that it will be more beneficial for you. And one more thing I'm going to tell you here, get the 10% discount on your subscription fees. You can use my promo code, that is DSP. Here next is where you can choose any one of this method to pay. Next, here is equal to 0 if AI is not related to BZ or AI BZ belongs to R. Here issue. So MIJ is equal to 1 if AI is related to BJ or AI BJ belongs to R, and is equal to 0 if AI is not related to BJ or AI BJ belongs to R. Right? Matrix relation MR, how we find here? Take some examples. Suppose this is your uh, relation. Example 1, A is equal to given, A is equal to 1 2 3 4 6, which is equal to B. Both the sets are same, A and B are same. A is related to B if and only if relation matrix MR. Okay, if and only if A is related to B, if and only if, we can find out A is related to B if and only if A divides B here. If and only if A divides B, then find the matrix relation MR. Okay, then find matrix relation MR. A divides B. Relation is defined, A divides B. So A divides B means here A is given. A is equal to our 1 2 3 4 6, right? So how we can find out the relation R? Relation R is given that A divides B, right? So here 1 divides 1, 1 divides 2, 1 divides 3, 1 divides 4, 1 divides 6, right? Again 2 divides 2, 2 divides 4, 2 divides 6, right? Then 3 divides 3, 3 divides 6, 3 divides 3, 3 divides 6, and also 4 divides 4, and 6 divides 6. Okay, your relation R is given with the defined relation, right? A is related to B if and only if the matrix relation MR is given as R is equal to 1 1 1 2 1 3 and so on. Now we can write the matrix MR here. So MR you can write now here 1 2 3 4 6. So exactly similar way 1 2 4 6. Here 1 2 4 6. Now, as 1 is related to 1, yes, so matrix entry is 1. As 1 related to 2, yes, so matrix entry is 1. 1 related to 3, yes, so matrix entry is 1. Here is also matrix entry is 1. Here is also matrix entry. Now 2 related to 2, 2 related to 1, no. So matrix entry is 0. 2 related to 2, yes. 2 related to 3, no. 2 related to 4, yes. 2 related to 6, yes. 3 related to 1, 0. Related to 2, 0. 3 related to 3, yes. 3 related to 4, 0. 3 related to 6, yes. 4 related to 1, 0. 4 related to 2, 0. 4 related to 3, 0. 4 related to 4 is 1. 4 related to 6 is 0. And here last entry 6 related to 1 is 0. Here is 0. Here is 0. Here is 0. The last entry. Right? Get it? Again. Now see. So if you want, you can write here matrix relation MR again here. So MR is equal to 1 2 4 6, right? 1 2 3 4 6. Exactly similar way from here. There is 1 2 4 6. 1 related to 1 1. There is 1, here is 1, here is 1, here is 1, here is 0, here is 0 1 0 1 0 0 1. It is your matrix representation. I hope you are clear how to write the relation R and how to represent the relation R by using this matrix. Now, here again given that A is equal to this, A is related to B if and only if A divides B, find the matrix relation MR. Okay, exactly similar way. Here first of all find out the relation R. R is equal to 1 divides 1, 1 divides 2, 1 divides 3, 1 divides 4, 1 divides 5, 1 divides 6, 1 divides 10, 1 divides 15, 1 divides 30. Right? Exactly similar way. Here you will get 2 divides 2, 2 divides 6, 2 divides 10, 2 divides 30. Right? Next. Here you get 3 divides 3, 3 divides 6, 3 divides 50, divides 30. Okay? Then 5 divides 5, 5 divides 10, 5 divides 50, right? 5 divides 30. Then 6 divides 6, 6 divides 30. 10 divides 10, 10 divides 30, right? 15 divides 50, 15 divides 30. Last is 30 divides 30, right? It is your matrix relation R. Now represented by matrix MR. Then you will get MR is equal to here 1, 2, 3, 5, 6, 10, 15. Exactly similar way 1, 3, 5, 6, 10, 15, 30. Right? 1, 1. Yes, 1, 10, 1, 1, 30. There are 2, 1. So 1, 1 divides 10. Yes. 3 divides 1. So 1, so 1, so 1, there 1. Divides 30. Right? 5 divides 1, 0, 0, 0, yes, 1, 0, yes, yes, 1. Divides 1, 0, 6 divides 2, 0, 6 divides 3, 0, 6 divides 5 also 0, 6 divides 6 is 1, 6 divides 10 is 0, 6 divides 15 is 0, 6 divides 30 is 1, 10 divides 1 is 0, 10 divides 2 is 0, 10 divides 3 is 1, 0, 1. That is 0, 0, 1, 1. There is 0, 0, 1. Right? Their matrix relation MR. Yeah? Their matrix relation MR. The given relation R. I hope you are getting it clear. Very simple topic actually this is how to find out the matrix relation MR. Now the graphical representation of a relation of a digraph. Okay, so graphical representation. Digraph it means it is directly given that. Digraph it means it is a directional graph. The directions are given for the graph. That is your diagram. Let A be a finite set and R be a relation defined on a set R, then R can be represented by a graph. The elements of a set are represented by circles or points, and these elements are known as nodes or vertices. If A related to A, then this can be represented by a loop around A. So A is your loop. And if A related to B, this can be shown by an arc from A to B. Here is A and here is B. Then we can see that here these arcs and loops are known as edges of a graph, and this graphical representation is known as graph. So this is your edge of a graph. That part we will see in the next chapter also, what you mean by graphs. This is your edges. Now diagram. Suppose R is relation given. Suppose A related to B, A be the set, A B C D, okay, is equal to B. Both are same. Related to B, A related to C, A related to D, Then this can be represented by using digraphs. Suppose I plot this, right? A, B, and D. Then A related to B is represented by using this pointing upward arrow. Then A related to C, digraph. A related to the digraph of a given relation. B related to C also. B related to this. So this is your digraph of a given relation R. Okay. This is your digraph for a given relation R. Now, okay. If A is equal to 1248, A related to B, if and only if A divides B, then find the digraph of a relation, right? So we will calculate the relation digraph. So first of all, for that, we will find out A is equal to, so A is 1248, and if A divides B, if and only if A divides B, then can say that here A divides B, it means here 1248, then A related to B. Here you will get A related to B as a, so A related to B relation R, first find out. A divides B. 1 divides 1, 1 divides 2, 1 divides 4, 1 divides 8, right? Then 2 divides 2, 2 divides 4, divides 8. 4 divides 4, divides 8, and 8 divides 8. Right? Here are, and find out the digraph of a relation R. First of all, we will write down the points. There is 1, there is 4, there is the nodes or vertices of a graph 1, 2, 4, 8. Now 1 related to 1, it gives you a loop. 1 related to this. Related to 4 is like this. 1 related to 8 is like this. You can write draw like this. 2 related to like this. Related to 4 like this. Okay? Then related to 8 like this. 4 related to 4 like this. 4 related to 8 like this. And 8 related to 8 like this. Right? This is your digraph of a relation R. Now next. So A is given if R is equal to AB such that A minus B is an integral multiple of 2. Right? Then A is equal to AB, then A minus B is an integral multiple of 2. Then find the digraph of the relation R. Right? So first of all, we will find out R first. Then we will draw the diagram. One thing I am going to tell you here, if the relation R is given, you can find out the matrix relation MR. If matrix relation MR is given, you can find out the digraph. And if the digraph is given, you can find out the matrix relation MR and relation R. So it is vice versa. If one thing is given, you can find out all the things. Okay. Diagram. The relation R. A minus B is an integral multiple of 2. So 1 minus 2 is not an integral. 1 minus 1. Yes. 0 is an integral multiple of 2. Then 1 minus 2, that is minus 1, is not an integral multiple of 2. But 1 minus 3, that is minus 2, is an integral multiple of 2. Right? Then you can write 1, 3. Then 1 minus 4 is not an integral multiple of 2. Now 2, 2, 0. Now 2, 4 is an integral multiple of 2. 3, 3, yes. 3, nothing. Then 4, yes. 4, 4, an integral multiple. Now 4, 1 is not, but 4, 2 is yes. And 3, but 3, 1 also. There will get 1 also, which is an integral multiple of 2. Right? This is your relation R. Now we can find out the digraph of this relation R. So we can plot here There is 1, 2, 3, 4. So 1, 1, and 3, 2, 2, 2, 4, 3, 3, 4, 4, then 4, 2, and 3, 1. I'm pointing the same age. I'm pointing like this. Right? So 1, 1, 1, 3, 1, 2 is your diagram of the given relation R. Diagrams for the given relation are suppose here A is equal to 1, 2, 3 and matrix MR is given. Then draw the diagram. Matrix MR is given when the matrix entry is 1, when both the elements are related. Right? So MR is given. It means here is your 1, 2, 1, 2. Right? So 1 is there, so 1 is related to 1. We can write down R first. R is equal to 1, 1. Then 1, 4. Then 2, 4. Then 2, 2. 3, 1. 3, 2. 4, 1. The relation R. Now we will draw the diagram of this relation R. So 1, 2, 3, 4. 1, 1. 1, 4. 4. 2, 2. 1. 3, 2. 4, 1. 4, 1. Here draw the diagram for the given relation. Sorry. Now the next inverse of a relation. Okay. And vice versa also. Suppose your sixth example we will see here. Suppose the diagram is given. Find the relation. Find the relation determined by the diagram and give the matrix. Its matrix. Right? 1, 2 arrow 3, 3. your diagram. Okay, are given. Find the relation determined by the diagram. Find out the relation. You can write the R. Here 1 is related to 1. Right? A is given. Here your A is equal to 1, 4, 6. Right? 3, 4, 5, 6. So here 1 is related to 1. 1 related to 2 related to here 1 related to 2 related to 3 related to that 3 related to 6. Check 4 related to 4. Then 4 related to 6. Right? 5 related to 5. And 6 related to 3 related to 1 related to. So everything is done. 3 related to 2, 2 related to 2, 3 related to 4, then 3 related to 6, 3 related 6 related to 2, then 4 related to 6. Okay, and now next that everything is covered. 1 related to 1, 1 related to 2, related to 1 related to 4, 3 related to 2, related to 6, 4 related to 4, 4 related to 6, 5 related to 5, 5 related to 2, and 2 related to 6. 2 related to 6. The arrow is related to 2. Correct. Arrow is like this. The diagram is given. You can find out the relation R and give its matrix. A matrix. Matrix MR. So R is given here 1 1 and 1 2 2 2 1 4 3 6 4 6 4 4 5 5 5 2 5 2 out the MR 5 6. Here is 1 6. 1 related to 1 1 here, 2 related to 1 down here the 1 1 3 2 6 here yeah 5 2 here is here right here 0 0 0 right your matrix relation MR. Now inverse relation. If R is a relation from A to B, then the inverse relation of R denoted by R inverse and is a relation from B to A. If R is defined from A to B, then R inverse is a relation defined from B, right? So X where Y is in B, X is and XY belongs to R. So this is your R inverse relation. Complement of a relation. Let A and B to two non-empty sets and a relation R from A to B is defined as R is equal to AB such that A belongs to A and B belongs to B. Then the complement of R, then R dash is denoted by R dash. The complement of R is defined as R dash is equal to here AB such that AB belongs to R and A is related to B if and only if A is not related to B. If A is related to B in R, then A is not related to B in R dash. And if A is not related to R, A is not related to B R, then A is related to B in R dash. Now, relation in a set. Let R be a relation from set X, then R is a relation, that is R is a subset of A cross A. Now, identity relation in a set A. Let A be any set, the relation identity A defined by AB belongs to AB such that A belongs to A, B belongs to A, and A is equal to B. It's called the identity relation. Thus, identity relation in a set A is the set of ordered pair AB of A cross A for which A is equal to B. It means A is equal to, here you will get 1 1, right? 1 1 R is a relation here. 1 1 2 2 3 3 all are identity relations. Suppose A is equal to 1 2 3, right? If A is equal to 1 2 3, then 1 1 2 2 3 are the relations, identity relation. Universal relation in a set A. Now the here universal relation, it means you will get, so let R be a set and R be any relation on set A, then R is a subset of A cross A, right? So then R is equal, if R is equal to A cross A, then the relation R is known as a universal relation. Now we'll see the types of relation. First, very important, that is reflexive relation. Let R be a relation in a set A, that is R is a subset of A cross A, then R is known as a reflexive relation if for all A belongs to A, ordered pair AA belongs to R. Right? For all A belongs to A, ordered pair AA belongs to R. That is every element is related with itself. Yeah? That is every element is related with itself. Means suppose A is given to A is equal to suppose 1, 2, right? Then R is a relation is given 1 1 1 3 2 2 3 3 and 3 2. So this relation R is a reflexive as every element is related with itself. Right? As every element is related with itself, therefore this is your reflexive relation. Next, symmetric relation. Let R be a relation in a set A, that is R is a subset of A cross A, then the relation R is said to be symmetric relation if AB belongs to R and BA belongs to R, which implies BA belongs to R. It means suppose 1 is related to 2, then 2 must be related to 1, then only that relation will be symmetric. But this is true for every pair of AB belongs to R. Okay? Must be true for every pair AB belongs to R. Compatible relation. A relation R on a set S is said to be compatible if it is reflexive and symmetric. As we know that what you mean by reflexive relation, what by symmetric relation. If R is symmetric relation, it means reflexive relation, it means every element is related to itself, and symmetric relation, it means AB belongs to R, then BA must be belongs to R. Okay. Now anti-symmetric relation. Let R be a relation in a set A and R is a subset of A cross A. The relation R is said to be anti-symmetric relation if AB belongs to R and BA belongs to R, which implies A is equal to B. That is, if A is related with B, relation R, then also is related with A with the same relation, then A and B are same. It means if you say that subset less than or equal to, greater than or equal to, are anti-symmetric relation. For if A is subset of B, B is subset of A, then which implies A is equal to B. Or A is less than or equal to B, B is less than or equal to A, which implies A is equal to B. So less than or equal to, greater than or equal to, and subsets are anti-symmetric relations. Transitive relation. Let A be a relation on a set A, that is, R is a subset of across A. Then R is called as transitive relation on a set A if AB belongs to R and BC belongs to R, which implies AC also belongs to R. It means A related to B, B related to C, then A is related to C. Then we say that that relation is transitive relation. Okay. Now we'll say here A less than or equal to B, less than or equal to C, then A must be less than or equal to C. So less than or equal to is then and transitive relation in this case. Okay. Similarly, subset is also transitive. We can prove that A is subset of B, B is subset of C, then A must be a subset of C. Yeah, transitive. Now, equivalence relation. In by equivalence relation, let R be a relation in a set A, then R is an equivalence relation on A. If and only if first one R is reflexive relation, that is, it means it possesses all the properties, that is reflexivity, symmetricity, and transitivity. Okay, so we know that reflexive A belongs, for all A belongs to R, then A is related to A, and R is symmetric, then for AB belongs to R, then BA must be belongs to R, and R is transitive relation, it means A related to B and B related to C, then which implies A is related to C. Now let's see this example. Let X is equal to 1 to 7 and R is equal to, here given, XY, such that X minus Y is a divisible by 3, such that X minus Y is divisible by 3, then show that R is an equivalence relation and draw a graph of R. It means digraph of a R. Okay, so X is given, so R is equal to XY. Then equivalence relation. So we can first of all find out the equivalence relation. X minus Y is divisible by 3. Okay, now first one, reflexivity. Reflexivity. Whether it is reflexive relation or not, that we will. So first, for the relation R is reflexive as X minus X is equal to 0 and 0 is divisible by 3, right? And 0 is divisible by, therefore X is related to X, therefore X is related to X, or X is related to X is divisible, reflexive relation X minus X is equal to 0 and 0 is divisible by 3, therefore X is related to X. Second part, that is symmetric relation. For X minus Y be divisible by 3, divisible by 3, divisible by 3, then X Y minus X, it, Y minus X will also be divisible by 3, also be divisible by, implies R is symmetric, implies R is symmetric. Third one, transitive relation. For A, B belongs to R, here X, Y, Z belongs to R, Y, Z belongs to R. Let X minus Y, A related to B, X minus Y is divisible by 3 and Y minus Z is also divisible by 3, also divisible. by 3. Now x minus z, which is equal to, you can write x minus y plus y minus z. Okay? You can consider x minus y plus y minus z. As x minus y is divisible by 3, y minus z is divisible by 3. So addition of these two is also divisible by 3, and this is nothing but x minus z, as x minus y and y minus z are divisible by 3. Therefore, addition of these two are also divisible by 3. Therefore, x minus z is also divisible by 3. X minus z also is divisible by. Therefore, we can say that the relation R is transitive, and which implies R is reflexive. Okay. Now we have to find out the relation of, it is digraph also we have to draw. The digraph is here. So there is 1, 5, 7. There 1, 3, 4, 5, 6, 7. Right? As 1 related to 4. So first of all we will find out R. 1 minus 1. Yes. Relation is 1, 1. 4, 4, 5. First of all, draw the relation. 1, 4, 4, 5, 5, 6, 6, 7, 7. Okay, that's 7, 7. Then next is x minus y. So 1 minus 2 is not divisible by 2. 1 minus 3 is also not 1, 4, 4, 1. Right? 6, 1, 7, 7, 1. Divisible. 2, 2. Then 2, 5, 5, 2. Right? 3, 4, 3, 6, 7, 7, 7, 5, 5, 6, 6. 1, 2, 3, 4, 5, 6, 7. 1, 1, 2, 2, 1, 1, 4, 4, 1, 1, 7, 7, 1, 2, 5, 5, 2, 3, 6. 4 7 7. Now every element is related with this. The digraph for the given relation. Now, the equivalence classes. Let A be any non-empty set and R be an equivalence relation on the set A, then equivalence class of this. The equivalence class of any element A in A is denoted by equivalence class of A or A bar or AA, and AA is a set of all those elements of A which are related to A. Equivalence class of A set of all those elements of A which are related with A. Suppose we consider the integers congruent to 0 modulo 5, the equivalence class of 0. I can write equivalence class of 0 congruent modulo 5, so 0, 5, 10, and so on. Minus 5, minus 10, minus 50 is equivalence class of 0. Right? Similarly, you can calculate equivalence class of 1 congruent modulo 5, so 1 minus 1 0, then 1 minus 6 5, that is congruent modulo 11, and so on. There is minus 4 and minus 9, so on. Equivalence class of 1. Equivalence class of now everything we will see in the next lecture. Now see equivalence relation we have to find out. First example we will get A is equal to given A is equal to ABC, suppose, and pi is equal to AB and C and D. Find the equivalence relation. Find the equivalence relation. First one, using a matrix equivalence relation, the matrix representation in A B. There is A, zero, 0, 1, 0, 0. There is 0, 0, 0, 1, 1. Right? This is your equivalence relation using matrix. You are getting it here. How to find out the equivalence relation, equivalence. Stop here. Next lecture we will there is transitive closure by using Virchow algorithm. Out the transitive closure by using Virchow part we will next lecture. Liking my video, please do like, share and subscribe.